Welcome to Cyclopod, showcasing work by early career geoscientists that is of interest to the cyclostratigraphic community. This podcast is made possible thanks to financial support of the International Subcommission on Timescale Calibration. Hi there, Happy New Year! After a short break, Cyclopod is back with its 7th episode already. And this month's Cyclopod is an episode with a lot of new features. It's the first Cyclopod episode that is recorded from my office here at the University of Münster. And today we don't have one, but we have two guests. And we are not going to talk about one cool cyclostratigraphy paper, but we're going to talk about two recent papers that deal with a similar topic. And that common topic is the productivity and the burial of carbonate-producing organisms in the oceans. And of course, a possible eccentricity imprint on this. So on the one hand, we have Boris-Karatsolis. He's a PhD student from Uppsala in Sweden, and he's the lead author on a paper in Nature Communications that just came out a few days ago. In that paper, he states that the end of the biogenic bloom in the early Pliocene was actually much more globally synchronous than previously thought. Moreover, Boris found that the end of the biogenic bloom corresponds to an interval with reduced seasonality because of a pronounced eccentricity minimum. On the other hand, we have Clara Bolton. Clara is a researcher at Serege in Aix-en-Provence in France, and she authored a recent paper in Nature. In that paper, Clara and her co-authors also state that eccentricity minima avoid seasonal extremes, but she found that, at least for the Pleistocene, this reduction in seasonality favors coccolith carbonate export and burial. So at first sight, we have two recent papers that come to the exact opposite conclusion. Boris finds less carbonate burial, but Clara finds more carbonate export during eccentricity minima. In this episode, we'll try to find out why we have this opposite response to astronomical forcing. So Clara, Boris, welcome to Cyclopod, and thank you very much for accepting this invitation for this double interview. How are you both doing?
I'm fine, thank you. It's really nice to be joining you both for this podcast.
Thank you very much for inviting me to your podcast, David. I think it's a great initiative and I have learned a lot by listening to the previous episodes. I'm doing pretty well and I'm really excited about our conversation today.
So the two of you actually have a lot in common. You are both very much into nanofossils, but you are also both very much into cyclostratigraphy. How did you discover that there are interesting links to be explored between cyclostratigraphy and nanofossil evolution and productivity?
So in my case, I guess as a micropaleontologist who's also very much into paleoceanography, it's impossible not to think about the links that there might be between which species are present at a given time, how abundant they are and how productive, and the climate changes that we know are happening in parallel. The idea that coccolithopore production or the dominance of certain forms might be linked to orbital cycles isn't a new idea, so there's quite a lot of ideas to build on in the literature.
In my case, I have been studying calcareous nanoplankton and nanofossils since I did my bachelor thesis. And during my PhD, I was introduced to the concept of cyclostratigraphy by you, David, actually, when I tried to produce an astronomically tuned age model for some IODP records. So after that, I got hooked in the whole topic and I started reading previous work that combines these two topics. And I started wondering how various well-established evolutionary events and changes in ocean primary productivity could be linked to cyclic changes in Earth's orbit, and if any abrupt event could be triggered by a specific orbital configuration.
So from your answers, it's pretty obvious that you share similar interests, but nevertheless, the approach that you took in your respective papers is very different. Can you summarize what exactly you did to quantify carbonate export?
Our approach can be considered more or less classic, especially compared to the other paper that we are discussing today. So our strategy was to collect as many globally distributed accumulation rate records as possible for this well-established interval of high productivity in various locations around the global ocean that is called the late Miocene to early Pliocene biogenic bloom. Since we were mainly interested on the synchronicity of events towards the end of the biogenic bloom, our main emphasis was on identifying which records had high-resolution age-depth models. And we did that by using an age model accuracy scoring system. After this filtering, we were left mostly with astronomically tuned low latitude records that we then standardized and compiled, first into groups for each one of the major oceans, and then into one combined low latitude paleoproductivity record. And what we saw, I think, was very interesting.
Thank you, Boris. And you, Clara, what exactly did you do in the paper?
Unlike Boris's, which is based on all different types of organisms that produce biogenic material, our study is based only on the dominant Noelorhabdocea coccolithophore group, which includes the dominant coccolithophore species present in the ocean today. And so coccolithophores are one of two main carbonate producers in the open ocean, and they also take up CO2 during photosynthesis. So they're involved in both the organic carbon pump, which I guess is what Boris is more trying to quantify, as well as the carbonate pump. So in our study, we quantified the morphology of coccoliths preserved in the fossil record and the abundance of these in thousands of different samples from different tropical sediment cores. So first, we measured the size and the mass of many individual coccoliths in these samples under the microscope, and we designed an index to assess the morphological diversity within each sample in this specific family. We then combined these morphological data with sedimentation rate, density, and age model data for each individual core, and we calculated the mass accumulation rate of this family of coccoliths over time. And so in the cores that we studied, this family represents about half of all of the coccoliths by mass. Because our work is mainly Pleistocene based, the accuracy of age models wasn't such a problem. In most of all the cores that we were worked on already had high resolution isotope stratigraphy based or other age models.
Yeah, I think Boris is pretty jealous of that. But pretty interesting approach, Clara. And what I also found fascinating is that you used artificial intelligence on over 7 million coccoliths. That is enormous. Can you tell us a bit more about that?
Yes, of course. So we used automated microscope methods and artificial intelligence techniques that have been developed in Serege by my colleagues Luc Beaufort and Yves Galli since the 1990s. And so basically microscope slides, which we still make manually in the lab, automatically imaged on the microscope, and the images are processed using a multi-layer neural network to classify the different morphotypes and species into groups. And so once the classification has been performed, the morphometrics of each individual recognized coccolith are carried out, including size and mass. So these methods really allow us to classify and measure high numbers of coccoliths per sample, and also to produce really high resolution records over long time periods. So here we have resolution of maybe a few thousand years over 2 to 3 million years for some of these records. That said, the data in the paper still represents many, many years of work that started with Luc and my participation in both IODP and Marion Dufresne cruises to collect these core samples.
Yeah, you can't leave it all to the computer.
No, definitely not. Fortunately.
Yeah, that's the fun part of the job, I
yeah.
guess. So Boris and Clara, in your two papers, low latitude seasonality plays a crucial role in the mechanistic path between orbital forcing and the accumulation of carbonates on the ocean floor. Boris, can you explain the processes that link forcing and response, as you highlighted them in your paper?
Yes, so our compiled records showed us that in all major oceans, an abrupt decrease in paleoproductivity occurred at 4.6 to 4.4 million years ago. We came up with what we believe is the most reasonable mechanism. The major system that provides low latitudes with nutrients through river runoff is the Asian monsoon. And the intensity of the monsoon has been shown to be controlled by the strength of seasonality that is pronounced during eccentricity maxima. So during strong seasonality, we have monsoon extremes that occur and are linked to increased alkalinity and nutrient supply in the ocean through river runoff. On the other side, on eccentricity minima, we avoid strong seasonality for prolonged periods of time. And according to some literature, low amplitude obliquity also contributes to a similar effect by decreasing the precipitation. Now, the interval from 4.6 to 4.4 million years coincided with a combination of a prolonged reduction in eccentricity and a shift to low amplitude obliquity. So we suggest that a causation effect exists and that this orbital configuration led to a lack of seasonality extremes and monsoon intensity, which in turn led to reduced supply of nutrients in low latitudes and therefore made it impossible for the biogenic bloom to be sustained.
Okay, but if I understand it correctly, Clara, you come to the opposite result. What is the mechanistic chain that you have in mind?
So in our study, we propose a cyclic recurrent response of coccolithophore evolution and productivity to eccentricity via its effect on seasonality, rather than a threshold response as suggested in Boris's paper. So we propose that when Earth's orbit is more circular, like today, so with lower eccentricity, the equatorial regions show little seasonal variation in oceanographic conditions and productivity, and so the range of ecological niches over a year is small. So in this scenario, species that are not very specialized tend to dominate all of the oceans, and these species tend to be highly productive, producing a lot of coccoliths, which is what we see reflected in our mass accumulation rate data. On the other hand, as eccentricity increases and more pronounced seasons appear near the equator, coccolithophores diversify into the wider range of ecological niches and evolve into many specialized species, but they collectively produce less limestone. Overall, the idea that highly productive blooming coccolithophore species tend to proliferate during eccentricity minima isn't a new idea, and it's consistent with the dominance of Gephyrochapsa huxleyi during today's low eccentricity configuration, and also with Gephyrochapsa data from the late Pleistocene published by Ros Rickaby and colleagues. High coccolith carbonate export during eccentricity minima is also consistent with the recent long calcium carbonate accumulation record published by Anna Joy Drury.
Cool, and another link to a previous podcast as well. That's amazing. So you both start from the fact that seasonal extremes are avoided for several 10,000s of years during an eccentricity minimum. But you come to the opposite effect on carbonate export as you are emphasizing different aspects of the Earth system. Could it be that productivity was more sensitive to alkalinity in the Plio-Miocene, but then became more sensitive to the availability of ecological niches in the Pleistocene?
I think that it could totally be the case. So we know that the climate system during the early Pliocene and the Pleistocene were very different. So in all aspects, from more pronounced northern hemisphere glaciation in the Pleistocene and the Central American Seaway being more closed, to probably different monsoonal dynamics and CO2 levels in the atmosphere, there were many climatic aspects that could influence the response of productivity to changes in the orbital parameters. But I think another key aspect, and maybe one of the main key aspects here, is the calcareous nanoplankton itself. So when we're talking carbonate accumulation rates, we're mainly talking calcareous nanoplankton, and the evolution of this organism since the late Miocene has been anything but boring. For example, the shift to smaller sizes in the dominant coccolithophore genera that occurred during the Pliocene could have totally changed the relationship between size classes and carbonate burial, as well as the mechanism of ecological niche generation. And for example, also the species that Clara mentioned, these Gephyrochapsids, were not even around when we see the change in productivity in the early Pliocene.
In our study, we found that we had increased coccolith morphological diversity during high eccentricity, which generally corresponded to low coccolith mass accumulation rates, and vice versa. So on the other hand, mid-sized species dominated at low eccentricity, but mass accumulation rate was higher. But what was really interesting was that we found that this cyclic response of coccolithophores on both 400,000 and 100,000 year timescales seems to be independent of ice volume and climate boundary conditions over the Pleistocene, including the intensification of Northern Hemisphere glaciation that occurred during our study interval. So in my view, there's no reason to think that things would be drastically different in the late Miocene and Pliocene ocean in terms of Noelahaptasy evolution, given that the Noelahaptasy coccolithophore group also dominated at that time. But of course, as Boris said, there have been big evolutionary size changes over these timescales. I guess one possibility that's worth considering is that coccolith mass accumulation rate may not always be linearly related to coccolithophore primary productivity. Perhaps our coccolith MAR records aren't necessarily always directly comparable to Boris's stacked PP records in terms of what they represent. Also, the large climate cycles in the late Pleistocene may well be masking the impact of coccolith for evolution on the carbon cycle on these kind of timescales, whereas in the Miocene warm world with smaller ice sheets, this kind of 400,000 year imprint may be more evident on the carbon cycle.
It's time for the number of the month. So let's take a step back from eccentricity, productivity, nanofossils, and think about a number that is relevant to our cyclostratigraphic community. And this month's number is 2. We now have almost 2 years of pandemic behind us. How did the pandemic influence your careers, Boris and Clara? And what are your resolutions for 2022?
So I guess from my perspective, the pandemic certainly impacted my scientific productivity as I have 2 young children. So working from home without childcare was pretty much challenging, to say the least. On the other hand, I'm lucky that our lab, Cerej, reopened partially quite quickly. So we were able to come into the office to work in a quiet environment. As for resolutions for 2022, I guess I'm trying not to be too hopeful, but I am certainly hoping that this year I'm going to be able to help my PhD students finish their research and manuscripts and defend their PhDs this year, despite all the difficulties they've faced during the pandemic. And I also have ambitious plans for my personal research, but of course, they kind of depend on school staying open for more than 2 days in a row.
I can relate to that. Boris, what about you?
Speaking from the PhD side of the story, doing my PhD, I think during the pandemic, it is pretty hard, and certainly the pandemic is influencing our careers. But apart, especially from the constant change in directives and rules and recommendations and the phases of the viral spread that caused work environment difficulties and mood swings. But I think the especially frustrating highlights for my PhD were the IODP expeditions in which I was selected to sail were postponed. But that being said, my family, friends, and the world in general has been through a lot during this pandemic time. So having been healthy with an extremely supportive and understanding supervisor and some data to continue doing my research, I consider myself lucky. And as for 2022, I plan to finish my PhD by this summer, and I hope that the pandemic will also end by then, if not earlier. And I still don't know what I will do after my studies, but I will start thinking about it when I'm closer to my defense date.
All right, back to the science now. The eccentricity pacing of the global carbon cycle has been the topic of dozens and dozens of papers over the last decades. Most of these studies, however, were based on carbon isotope records. In your papers, you are explicitly not using carbon isotopes. Why might that be an advantage? What can be gained by giving carbonate export a more prominent place in the assessment of the role of astronomical forcing on the global carbon cycle?
I'm not an expert in delta 13C, but I remember from my student years that I was constantly confused on what really influences this proxy. And that is very sensitive and controlled by many different parameters. So I think there might be indeed an advantage, especially for the biogenic bloom, that carbonate accumulation rates and other biogenic sediment accumulation rates were the way they described this event. So it is a straightforward way to investigate the course of events for this interval. And I think that when it comes to changes in calcareous nanoplankton productivity, when you know they are the main producers of these carbonates, so you can see more directly the changes by studying the accumulation rates. You are losing, of course, a bit of the bigger picture, but you are eliminating also many potential mechanisms that could explain changes in delta 13C. So I think in this specific interval and for this specific cause, it is beneficial to use the accumulation rates.
So you're right, David, that many foraminifal delta 13C records, as well as carbonate content records from the Pleistocene and the Neogene, show and even before, in fact, show very strong eccentricity pacing. But for now, there's no consensus on which exact mechanisms are driving this change in the ocean carbon cycle. So in our study, we tried to focus explicitly on the potential contribution of coccolith carbon exports and how their evolution with related changes in production may have led to cyclical impacts on the carbon cycle. Future work on coccolith carbon isotope signatures on these kind of timescales might help us to try and understand the link between foraminiferal carbon isotopes, ocean delta 13C and coccolith delta 13C and carbonate burial, because of course, on top of the fractionation impact driven by productivity and calcite formation is organism-specific or species-specific vital effects in terms of fractionation that kind of complicate the understanding of the signal.
Clara, if I may, I'm going to cite a sentence from your paper, and that is, we posit that eccentricity pacing of phytoplankton evolution contributed to the strong 405,000-year cyclicity that is seen in global carbon cycle records. So that's a cool quote, and interestingly enough, the strongest imprint of 405,000-year eccentricity in delta 13C benthic records is found in the Miocene, so before and during the biogenic bloom. So that somehow is a real nice connection between your two papers. Clara, can you elaborate a bit more on how the 405,000-year cycles and phytoplankton evolution could have been linked?
Yes, I can certainly try. So, of course, coccolithophores are only one of many plankton groups that collectively impacted the ocean carbon cycle, and terrestrial carbon inputs also influence whole ocean carbon isotopic composition. But in theory, if higher coccolith carbonate export did correspond to higher total primary productivity, this could explain the higher delta 13C signal in the surface ocean and the higher calcium carbonate accumulation that are seen during Miocene eccentricity minima. So it would certainly be interesting and relevant to look in detail at the vetted late Miocene primary productivity records that Boris has compiled and included in his stack to see if there is a covariation on 400,000-year timescales between carbon isotope records and primary productivity.
Boris, in your paper, you are sharing your vision on what needs to be done in the future to further disentangle the causal connection between eccentricity and carbonate production. Of course, you mentioned assemblage studies, but you also mentioned the possibility of running a coupled climate by a geochemical model with time-varying orbits. How would you design such a model experiment?
Yeah, I would certainly consult model experts since I know little about how to design exactly a numerical model, but with my little knowledge on the topic, I would mainly be interested in time slices with varying orbital parameters. So two main scenarios, for example, could be one with high eccentricity and obliquity, and the other one with a minimum eccentricity and obliquity. And what I would mainly be interested in is the effect of these two scenarios in monsoonal precipitation and runoff. So the difference in values between the two scenarios could potentially give us an indication of what the lack of seasonality extremes could mean for the nutrient budget. And after that, it would be interesting to also see the response of the phytoplankton to different levels of nutrient availability, as well as the ocean circulation changes, because the extent of the decrease that we see in productivity in the early Pliocene should have been controlled by an ocean circulation component too, because it happens simultaneously in all low latitudes. So that is my simplistic version. Of course, I think there is a lot more to numerical modeling than just that, but this is where I would start from.
I mean, I agree that it will certainly be fascinating to use modeling tools to try and really understand the relation between the cyclical changes that we think are due to varying orbital parameters and the long-term threshold changes that may also be due to certain orbital configurations like the end of the biogenic bloom, and how these two things can be reconciled. In our study, we looked at changing eccentricity configurations under different precession conditions, but under constant obliquity.
Thank you, Clara, for this perspective on what we can learn more by using numerical Earth system modeling. Thank you, Boris, as well, for sharing your story on the end of the biogenic bloom. It seems like we are just at the beginning of understanding how phytoplankton reacts to astronomical insolation forcing. And at this point, I would like to also thank our audience for listening to this 7th episode of Cyclopod. I really enjoyed talking to Boris and Clara about their respective nature papers. From this episode, I take away a number of messages. First, one needs to sample ocean sediment at very high resolution to understand the response of ocean productivity to astronomical forcing. Second, we need very, very good H-depth models. Boris struggled with that, and I think his ranking system was a very clever idea. And third, with a little bit of help of computers, we can do amazing science. Thanks, Clara, for sharing your neural network story. I'm very much looking forward to the follow-up papers that build upon the work of Boris and Clara. Thank you for listening, and see you next time.